So today we'll be starting with forces that govern microevolution. Now, if we think about the forces that govern microevolution, now let's look onto the left side of the table. Mutation is the source of new allelic variation. So we all are aware of the fact that random mutations within pre-existing genes introduce new alleles into population, but at a very low rate. Whenever there is a mutation, the mutation may be beneficial, neutral, or deleterious. So mutation do affect the allele frequency of a population. Other mechanisms that alter existing genetic variation is natural selection. This is a phenomenon in which certain phenotypes have greater reproductive success compared to other phenotypes and these phenotypes are preferably selected by nature. So natural selection is based on the reproductive success of a particular phenotype, and certain phenotypes are preferred over others. When we are talking about genetic drift, we will be dealing with all of these topics individually. Just to summarize what are the forces that govern microevolution, I'm going over them. Genetic drift is the genetic variation from generation to generation due to random sampling. Allele frequencies may change as a matter of chance because sometimes from one generation to another, and this happens all the more if the population is small. Since small populations, this phenomenon of genetic drift occurs. So when we will be discussing genetic drift, I'll explain in detail how a genetic drift causes change in allele frequency in a small population. Then there's this migration. Migration can occur between two populations. People coming from one population, when moves into another population, they contribute to the alleles of the population to which they're moving in. So introduction of migrants in the recipients may change the allele frequency of the recipients. And finally, in natural population, as Hardy-Weinberg had postulated that mating should be random, but we are all aware that in natural population, the random mating phenomena doesn't occur. It is usually a mating by choice, where individual selects mates based on their phenotypes or phonetic lineages. This is also true for the animal world. So now one by one, we'll look into how these forces actually is changing the allele frequency in a population, keeping in mind the baseline model of Hardy-Weinberg equilibrium. To recapitulate, when we studied Hardy-Weinberg equilibrium, we had said that the Hardy-Weinberg equilibrium is applicable in case of populations which are finitely large, in which we see the phenomena of random mating and the forces of nature, that is migration, mutation, and natural selection, are not occurring in the population. But that is a hypothetical population. When we are talking about real populations, or populations, natural populations, these factors do occur. And if these factors occur, how does the allele frequency change from one generation to another? So we will start with the first one, that is migration, and how migration causes genetic variation. So when we are talking about migration, this particular word becomes very important. The concept of gene flow. Now let us imagine there is a population. Let us say this population is X, and we have a population. Let us imagine this population to be Y, okay? And there is an allele which is capital A. The frequency of capital A in population X is PX, and the frequency of capital A in population Y is PY. At any given moment, imagine 20, let us imagine 20 individuals, or let us put it in a alphabetical connotation. M individuals are moving into population Y. So an event of migration is occurring where M amount of individuals are moving from population X to population Y. Population X is known as the migrants. Population Y is known as the recipients. Now, the moment there is a phenomena of migration occurring and M individuals has moved into Y, this population is now referred to as the conglomerate population. We have to consider the conglomerate population as one. Let us imagine that one represents the total number of conglomerate population. Now this conglomerate population contains the original residents of population Y and some migrants from population X. So if I say that M is the number of migrants in this conglomerate population, then the number of residents in this population is 1 minus M. So M individuals has migrated to the residential population Y. And after the phenomenon of migration, I said that this population is now the conglomerate, which is represented by 1. And among 1, now I can say M is the amount of migrants and 1 minus M is the amount of the residents. So a phenomena or an event of migration has occurred, and what we got a conglomerate population. Now let me right, so we had this population X, we had this population Y, and I said M amount of individuals migrated to population Y, and now this population has become a conglomerate population. Which is now represented as 1. So this population contains M individuals of migrants and 1 minus M individuals of residents. So this much we have got. Now let us come to the allele frequency. As I said, let capital A frequency be Px. Okay. Let capital A frequency in the Y population be Py. So if M individuals are moving, then the amount of allele that has moved from population X to population Y is MPX. Capital A has a frequency of Px in Px is X. I have written X and Y to make you understand that Px symbolizes capital A frequency in X population. Py, the Y symbolizes capital A frequency in the Y population. Remember, X are migrants and Y is residents. Remember that. So if capital A frequency is Px, now at any given moment, I'm saying you that M individuals have moved into the conglomerate. So how much of the migrants have contributed to the A allele in the conglomerate? Because in the conglomerate also there is this capital A allele. And let us write this capital A allele as P prime. For the conglomerate, let us write it as P prime. So the frequency of capital A allele in the conglomerate is P prime. Now, in the conglomerate population, the capital A allele has been contributed by the migrants as well as the recipients. So, if, as I said, if M individuals are moving into Y population from X population, then the amount of capital A allele that has been added is MPX. So, in the conglomerate, we are having this MPX fraction of capital A allele from the migrants. Now, 1 minus M is the amount of residents present in the conglomerate. They had a frequency of capital A allele, which was PY. So the total amount of capital A allele with respect to the residents will be 1 minus M PY. So you can understand that after the event of migration, P prime, that is the frequency of capital A allele in the next generation, is becoming MPX plus 1 minus M PY. Thus, an event of gene flow has occurred. Allele has moved from the migrants to the recipients. This movement of alleles from the migrants to the recipients has brought a change in the allelic frequency of the recipients, and the population has become conglomerate, and the change in allelic frequency is represented by P prime is equal to MPX plus 1 minus MPY. So this is, I just explained you in my line diagram. So this was the figure. This is the frequency of, this is population 1, migrating population. This is the residents, population 2. The moment an event of migration is occurring, as I said you, the population is becoming conglomerate population. Within this conglomerate population, we are having M individuals which are migrants and 1 minus M individuals which are recipients. The allelic frequency of the migrants was PX. So the total capital A allele present now in this conglomerate population from the migrant is MPX, and the total capital A allele contributed by the residents, which are 1 minus M in the conglomerate, is 1 minus M PY. So that will be the frequency of capital A allele in the next generation. So if you have understood that in the next generation, what we are getting after an event of migration is that the frequency of capital A in this case will be MPX. This is the amount of capital A allele contributed by the migrants plus 1 minus M within bracket into PY. This is the frequency of capital A allele contributed by the recipients. And these are the symbols. M is the proportion of migrants. 1 minus M is the proportion of residents. PX is the frequency of A allele in migrant. PY is the frequency of the A allele in resident. And P prime Y is the frequency of the A allele in the conglomerate. That is, after the event of migration has occurred, it is the frequency of capital A allele in the final population. So we have deduced this equation. Very similarly, when we are talking about the recessive allele, this was the dominant allele. So regarding the dominant allele, we derived that P prime Y is equal to MPX plus 1 minus MPY. Similarly, regarding the recessive allele, we can say Q prime Y is equal to MQX plus 1 minus MQY. There's one more thing that needs to be known is that for problems, we are not going to deal with problems. We are just going to go by the derivations only. When you need to calculate the value of M, how will you calculate the value of M? It is a number of migrants divided by the total number of individuals in a conglomerate population. For example, let me give an example. There are 20 individuals which are migrating, and there are 80 individuals which are present in a place. These 20 individuals are migrating here. So the moment they migrate, as I said, they are becoming a conglomerate population. The total number of individuals in this population is now 100 because 20 migrants, 80 recipients. So M will be 20, that is a proportion of migrants by the total number of individuals, that is 0.2. So that is how we calculate the value of M. Now, let us come to another part. Thing is that we have understood that we saw the phenomena of migration, right? We saw an event of migration. There was PX, some individuals, M individuals migrated to PY. We are now having a conglomerate population where the frequency of the capital A has become P prime Y. So PX is the frequency of capital A in migrants. PY is the frequency of capital A in residents. And P prime Y is the frequency of capital A in the final population. Okay. Now, you can understand that PY was the frequency of the population, the resident population before migration. So capital A was PY in this resident population. This is the resident population before the event of migration. Now, since some individuals have migrated to the residents, now what we are getting, we have seen that there's a change in frequency occurring. A change in frequency occurring. PY has become P prime Y because an event of migration took place. So how much did the allelic frequency change after an event of migration? So once an event of migration is occurring, what is the change in the allelic frequency of the resident population from that of the final population? So we can write P prime Y minus PY. It gives us del P, that is the change in allelic frequency as a result of migration. So that is what we have written here. And we just now derived, I showed you how to derive P prime Y is equal to MPX plus 1 minus MPY. We simply substitute this value in P prime Y. And on substituting this value in P prime Y, what we are getting something like this. So you open up the brackets. Once you open up the brackets, you can see this one cuts off. So change in allelic frequency is del P is MPX minus PY. So after an event of migration, what we saw, there was a change in allelic frequency between the residents and the original population. And the change in allelic frequency is denoted by the symbol delta P is equal to MPX minus PY. So now we can say that del P, so this is another important derivation, the change in allelic frequency after migration. And to point out certain facts, that this change in allelic frequency after migration depends on two factors. As you can see, look into the equation. What are the two factors? One factor is evident. Factor one, that is how much amount of migrants are actually entering into the resident, or how much amount of migrants are present in the final population. So the amount of migrants is an important factor that determines the change in allelic frequency from migration. And the second factor is the difference between the two alleles in the original two population. That means the original two population were the migrants and the residents. We had a PX and a PY. If PX is equal to PY, that means the frequency of capital A in the migrants equals to the frequency of capital A in the residents, then in this equation you see we'll get a value Px minus Py is equal to 0 or del P is equal to 0. In that case, even though an event of migration will occur, there will be no change in allele frequency. So as I said, the two important things on which the change in allele frequency depends is M, that is the number of migrants present in the original population, and the difference in the allele frequency between the migrants and the residents. In order to bring a perceivable change in the allele frequency, the populations must, that is the migrants and the recipients, must differ in their allele frequencies. Another important thing you must keep in mind that with continued migration, if this phenomena goes on, migration is taking on and on, Px and Py gradually tend to become similar. There will be a tendency that both the values Px and Py tends to become similar. That means del P gradually becomes 0. As a result, as I said, the change in allelic frequency due to migration decreases. And a time will come when the allele frequencies in the two populations will be equal and no further change will occur. But this phenomena is only possible if we are not considering the other forces of evolution, such as natural selection or mutation. So while studying migration, till now, we have understood two derivations. One is the allele frequency in the next generation after an event of migration. That is, we have understood to derive the P prime Y and the Q prime Y value. And we also understood how the change in allelic frequency occurs as a result of migration by the formula del P is equal to MPX minus PY.